Hi everyone. Today we are going to talk about cross-validation technique. There is always a need to validate the stability of your machine learning model. I mean, you just can't fit the model to your training data and hope it would accurately work for the real data it has never seen before. You need some kind of assurance that your model has got most of the patterns from the data, and it's not picking up too much on the noise, or in other words, it's low on bias and variance. So let's understand cross validation. This is the process of deciding whether the numerical result quantifying hypothesized relationship between the variable are acceptable as descriptions of the data is known as validation. Generally, an error estimation for the model is made after training, better known as evaluation of residuals. In this process, a numerical estimate of the difference between the predicted and original response is done, also called training error. However, this only gives us an idea about how well our model does on data which we use to train it. Now it's possible that the model is underfitting or overfitting the data. So the problem with this evaluation technique is that it does not give an indication of how well the learner will generalize to an independent or unseen data set. Getting this idea about our model is known as cross-validation. Cross-validation is a statistical technique for testing the performance of machine learning model. In particular, a good cross-validation method gives us a comprehensive measure of our model performance throughout the whole dataset. All cross-validation methods follow the same basic procedure. Divide the dataset into two parts, training set and testing set. Train the model on training set, evaluate the model on testing set. Optionally, repeat step 1 to 3 for different set of data points. More thorough cross-validation method which includes step 4, since such measurement will be more robust to biases that may come with selecting a particular split. Bias that comes from selecting a particular part of the data is known as selection bias. Aside from selection bias, cross-validation also helps us avoiding overfitting. By dividing the data set into train and validation set, we can concretely check that our model performs well on data unseen during training or not. Without cross-validation, we would never know if our model is amazing worldwide or just on our sheltered training set. With all that theory being said, let's take a look at three common cross-validation techniques. Okay. The first one is holdout method. Holdout cross-validation is the simplest and most common. Very simply, split the data set into two sets, train and test set. The train and test data must not have any of the same data points. Generally, this split will be close to 85% of the data for the training and 15% of the data for testing. The diagram below illustrates how holdout cross-validation would work. The disadvantage of using very simple holdout cross-validation is that we only need to train one model. If it performs well enough, we can go ahead and use it in whatever application we intend to. This is perfectly suitable as long as your data set is relatively uniform in terms of distribution and difficulty. The danger and disadvantage of holdout cross-validation arises when the data set is not completely even. In splitting our data set, we may end up splitting it in such a way that our training set is very different from test, or easier or harder. Thus, the single test that we perform with holdout is not comprehensive enough to properly evaluate our model. We end up with bad things like overfitting or inaccurately measuring our model's projected real world performances. So next comes is k-fold cross-validation. Using k-fold cross-validation, we will help you get past a lot of drawbacks that come with using holdouts. As there is never enough data to train your model, removing a part of it for validation poses a problem of underfitting. By reducing the training data, we risk losing important patterns or trends in data, which in turn increases error induced by bias. So, what we require is a method that provides ample data for training the model and also leaves ample data for validation. K-fold cross-validation does exactly that. In k-fold cross-validation, the data is divided into k subsets. Now the holdout method is repeated k times such that each time one of the k subset is used as a test set or validation set, and the other k minus 1 subsets are put together to form training set. The error estimation is averaged over all k trials to get total effectiveness of our model. As can be seen, every data point gets to be in validation set exactly once and gets to be in training set k minus 1 times. This significantly reduces bias as we are using most of the data for fitting, and also significantly reduces the variance as most of the data is also being used in validation set. Interchanging the training and test set also add to the effectiveness of this method. As a general rule and empirical evidence, k is equal to 5 or 10 is generally preferred, but nothing fixed. It can take any value. For example, if we set k is equal to 10 as in the example below, then we will train 10 models. Each model will be trained on a unique training set, the part shown in the blue color. Each model will also be tested on a unique test set, part shown in the green color. The only possible drawbacks for this method is that we gain robustness by increasing k. We also have to train more model, a potentially tedious and expensive process. The next step is repeated random subsampling. Repeated random subsampling is perhaps the most robust of cross-validation methods. Similar to k-fold, we set a value for k which signifies the number of times we will train our model. However, in this case, k will not represent the number of equally sized partitions. Instead, on each training iterations, we randomly select points to be for the testing set. The number of points we select will be a certain percentage we set for the testing set. For example, if we select 15%, then on each training iterations we will randomly select 15% of the points in our data set to be set aside for training. The rest of the procedure continues same as k-fold. Train on your training set, test each model on its unique test set, average out the result at the end to obtain a final accuracy. The clear advantage of this method over K-fold is that the proportion of train test split is not dependent on the number of iterations. We can even set a different percentage for the test set on each iterations if we wanted to. Randomization may also be more robust to selection biases. The disadvantage of this method is that some points may never be selected to be in the test subset at all. At the same time, some points might be selected multiple times. This is the direct result of the randomization. Yet with K-fold, there is a guarantee that all points will at some time be tested on. So cross-validation is a very useful technique for assessing the effectiveness of your model, particularly in cases where you need to mitigate overfitting. It's also of use in determining the hyperparameter of your model, in the sense that which parameters will result in lowest test error. This is all the basic you need to get started with cross-validation. You can get started with all kinds of validation technique using scikit-learn. That gets you up and running with just few lines of code in Python. Thank you for watching video.